Okay, this video is on the equations in P6. Now there aren't that many equations in P6, but there are a couple that you have to remember that you're not given. So starting with remembering that in P4 we did that resistance is voltage divided by current. That equation could be used sort of at any point, because the first thing we have to do is be able to calculate the resistance of resistors that are in series, so one after the other, and the resistance of two components with resistance that are in parallel, like so. Now just to point out, these don't have to be fixed resistors. It could be any type of resistor, so a thermistor, an LDR, or it could be like a bulb or an LED, or any electrical component that has resistance. So we've got R1 and R2, and I'm going to do the same here, R1 and R2. So resistors in series is very simple. The total resistance is just each resistor added together. Okay, and that's it. There's nothing more to it than that. The resistance or total resistance of an object in parallel is a little bit more tricky. That is 1 over the total resistance is 1 over R1 plus 1 over R2, and obviously if you've got more components you just continue that pattern. So remember, when you do 1 divided by R1 plus 1 divided by R2 and you add them together, you must then remember to do 1 over your answer to give you the total resistance. So don't miss that step, please. Just as a little point to bear in mind, if I had a circuit where I have a parallel component, so I've got R1, R2, R3, what I do here is work out the parallel components separately first. So I do 1 over R2 plus 1 over R3, do 1 over the answer to give me the total resistance, that bit, and then treat this as a single resistor. So I treat that as a single resistor, and then I can just add it directly to R1. So if you've got a series and a parallel bit, that's how you deal with it. The next bit is linked to logic gates and transistors, and it's the equation for a transistor. So in a transistor, circuit symbol is like this. So we have the collector, and we have the base, and we have a current coming into the base and a current coming into the collector, and then we have the emitter. Now this is a very simple equation. The equation is simply the current in the emitter is the current in the base plus the current in the collector. So the current coming in here and here adds together to give you the current in the emitter. That's very simple. Just to bear in mind how transistors work, for a transistor to work, there has to be a current coming in at the base, and effectively in order to turn the transistor on. So you have a very, very small base current, which then allows a much larger current to flow through the collector and then it be emitted. But if you don't have a base current, the transistor won't be switched on. There will be no current flowing through at all, which is how it turns an on signal into an off signal, effectively. And logic gates are combinations of transistors. So an AND gate, for example, is two transistors in series, like so. An OR gate is 2 in parallel. So just bear that in mind. And the next major topic that we have equations in is transformers. So in a transformer, the setup for a transformer is that you have an iron core and you have 2 coils of wire. You have the primary, or the input, and you have the secondary, or the output. And in this case, because there are more turns on the secondary coil than there are on the primary coil, this would be a step-up transformer. If there was less, then it would be a step down, and if they were equal, it would be an isolating transformer, which job is to isolate mains electricity in order to prevent electric shocks. So the equation is that the number of turns on the primary coil divided by the number of turns in the secondary coil, which is a ratio, is constant to the voltage on the primary coil over the voltage on the secondary coil. So that's our basic equation. Now what we can do with this is, since we assume that a transformer is 100% efficient, the power input must be equal to the power output. We make that assumption. So we know that electrical power is current times voltage. So we can have the current on the primary times the voltage on the primary is the current on the secondary times the voltage on the secondary, assuming that it's 100% efficient and that all the power that's input is also transmitted. And so that's our second equation, and what I can do is I've got an equation here in terms of number of turns and voltage. I can also have one in terms of voltage and current. I can have one in terms of number of turns and current. And just the thing to remember about that is it's the only equation where you don't have primary on the top in both cases, because you've got number of turns on the primary is over the number of turns of secondary is equal to the current in the secondary over the current in the primary. So you've got those three equations. This is the most important. Another thing they will do with power in transformers is you're expected to be able to calculate the power lost. And what we do in power loss is power loss doesn't depend on voltage. It does depend, however, on the current that flows through the device and the resistance. So what we do is we substitute in Ohm's law in here for voltage, and so we get that power loss is equal to I squared R. So it depends upon the current squared and the resistance. That's what determines the power loss. So as another equation, that one's particularly important. Remember, if the current increases, the temperature increases, and that's what increases the resistance. And obviously, if the resistance is higher, you'll have a greater power loss. So in terms of equations, that is it for P6. Most of the other knowledge in P6 is being able to explain each of the different electrical components, IV characteristics, logic gates and the outputs that come from those. Also the difference between how motors and generators work, and obviously transforming and then charging as the last topic.